Good afternoon, everyone. Welcome to another round of our series of the wonderful world of heat pipes. Today we are going to focus on the energy code, ASHRAE standard 90.1, and how heat pipes can be utilized to meet said energy code. So topics to be covered today, of course we're going to start off with just a quick heat pipe refresher just to remind everyone how they work. And then, of course, we're going to focus on ASHRAE standard 90.1 and get into all the different energy recovery options that are available. Spoiler alert, one of those is a heat pipe. And then we're going to focus on making them controllable to really optimize that heat pipe selection and get the best bang for your buck. And then finally, we'll focus on some different installation features that are available. So this screen may be very common to everybody, but this is your basic heat pipe, a single tube, what we call a single tube circuit. If you've seen the swivel sticks that dip into the cup of hot water and get hot really fast, that's exactly what this is. Basically, you got a tube, you got refrigerant inside. As soon as you apply heat to one end, the refrigerant on that end is going to pick up that heat and boil. As soon as it flashes to a vapor, that creates a pressure differential inside, and that vapor is going to naturally go to the other end of the heat pipe, then give off the heat to the cooler air stream, condense back into a liquid, and then go back to the other side. So it's a passive device, no pumps needed. It's just transferring heat from one end to the other. And it's the phase change of that refrigerant that gives the heat pipe its effectiveness. Now, we at Heat Pipe Technology don't use that single tube circuit. There are heat pipes out there that do. We use what we call a loop circuit, and this graphic is showing what one individual loop circuit would do. So picture the air moving in and out of the screen, and if you apply heat to the right side there, well, actually, let's say if there was no temperature differential or no air, we would just have refrigerant sitting at the bottom of that loop. As soon as you apply hot air to the right side, the refrigerant on that side is going to pick up the heat and boil. It's going to go up that loop on the right side, travel to the other side, then give off the heat, condense to a liquid, and keep going around, in this case, in a counterclockwise loop. And if it's air-to-air energy recovery, if that season changes and that hot air on the right side becomes cold air, then the refrigerant is just going to change directions all by itself. So we take these loop circuits and stack them so many high, so many rows deep, so long, depending on the size and what's needed out of it. They're all a bunch of individual loop circuits, so they're all acting independently, but when you add them all up, they're all acting together. So it looks like a coil, except they're all a bunch of individual heat pipe, in our case, loop circuits. The loop allows us to get away with using smaller half-inch tubes, so we use half-inch copper tubes in all of our applications. What you're seeing here is just side-by-side energy recovery, which is a very common means for energy recovery. There's other devices out there to do it. We just happen to use a heat pipe to move heat from one airstream to the other as needed. If it's hot outside, we move that heat over to the exhaust to pre-cool it. If it's cold outside, we take heat out of the exhaust air and move it over the outside air to preheat it. We also do something a little bit different. We take that same loop, but instead of sending that loop, the one end of the loop to another airstream, we'll wrap it around the coolant coil and use it as reheat. So this is what we call a wraparound heat pipe. It's the same loop, except instead of going horizontally all the way across from one airstream to the other, it's just bent into kind of a U shape around the coolant coil. But inside, it's doing the exact same thing. So why would you use a wraparound heat pipe? Well, first let's start off talking about ASHRAE standard 62.1. That's your indoor air quality ventilation standard. And the one thing I want to point out is that, and I'm sure everyone here knows, is that we always have to keep the space below 65% relative humidity. This is why most designs are in the 50% to 55% RH range from a set point in cooling season, because that gives you plenty of cushion, so you don't chance hitting that 65% mark and getting too humid and uncomfortable for everybody. And not to mention risk more chance of mold growth and nasty stuff like that. The tricky days are when it's relatively cool outside and maybe it's raining and you're bringing in a bunch of that outside air. That thermostat may tell you that it feels great and you don't have to do anything. But the RH side, or if there's a humidistat, it's going to tell a different story and tell you that no, temperature-wise it feels great, but it's getting way too humid in here. We got to wring out some of this moisture. So age-old solution is let's wring out the moisture, overcool the air, so to speak, make sure we get it down to the dew point we need. But then it's probably too cold, so we have to reheat the air back up so that we're not just meeting the humidity set point, but also the temperature set point out in the space. And that's really the key. It's not just temperature, it's not just humidity, it's both. This is also a common control strategy for part load. You still want to get to that same dew point, but you're going to reheat the air based on the load out in the space. And as the load drops, you're going to need more and more reheat to maintain the same set point. Problem with this is that though you need that reheat to keep it comfortable, that reheat isn't free. You do have to pay for it, and it can get expensive. Not to mention ASHRAE standard 90.1 won't allow you to simultaneously cool and heat unless they say that heat is it's site recovered. And 90% of it, according to 2013, if you're a state that uses an older version of 90.1, it's like 75%. But either way, the majority of that heat must be site recovered. So what site recovered heat? Hot gas reheat, if you got a DX system, would be considered site recovered heat. It's waste heat that you're utilizing for reheat. Of course, if you got a chill water system, then it's a different story. You don't have the luxury of hot gas reheat. You've got to find some different solutions, and that's where the wraparound heat pipe comes into play. So again, we've got a heat pipe in the incoming airstream. It's hot. That refrigerant's going to pick up the heat and boil and go to the other side, except in this case, the other side isn't another airstream where we're simply dumping that heat. In this case, we're wrapping it around the coolant coil and just reusing that heat as reheat. So it is site recovered heat. We've not only reduced the load on the coolant coil by pre-cooling that air, but we're giving you that free reheat as well. And even for a DX system that could use hot gas reheat to give you that free reheat, that is simply waste heat, where in this case we're actually pre-cooling to go get it. So we're actually going to reduce the load on both sides of the coolant coil instead of just reducing that reheat. So let's look at a site chart. Here's that same process, but on a site chart. If we did not have a wraparound heat pipe in there, you had 80-degree incoming air and you had to get down to a 50-degree dew point off the coolant coil, you would have to have a coil that would go all the way from point A through point B, ride the saturation curve down to point C, and then reheat it back up as necessary. The wraparound heat pipe, on the other hand, is going to do what from point A to point B. It's going to pre-cool that air for you. So now, as you can see, it's either a smaller coolant coil, less GPM, less compressor, whatever it is, to get the same amount of cooling down to a 50-degree dew point. And then, of course, whatever heat was pre-cooled out of the air is just being wrapped around and dumped in as reheat, as shown from point C to point D. The flip side here would be if you had the same coolant coil in there that without the heat pipe was going all the way from point A to point C, the sensible cooling that the pre-cool portion of the heat pipe does allows that coolant coil to do more latent cooling. So instead of just getting down to a 50-degree dew point, it's able to ride the saturation curve a little bit longer and get down to perhaps a 48-degree dew point or something like that. and still get you the free reheat. So whether it be reducing the cooling load with free reheat or depressing the dew point further plus the free reheat, or a combination of the two, that's what the wraparound heat pipe has to offer. And we call ours the dehumidification heat pipe, or DHP. So when you see model DHP out there, that's what it stands for. So the kind of applications that we most commonly get into, first of all, and I got it bolded there because from an energy standpoint, it's all about the reheat. So whenever reheat is being needed to control humidity, for part load control, the wraparound heat pipe should always be the first thing that comes to mind, because not only, again, is it going to give you free reheat, but it's going to pre-cool while it's getting it. And the more reheat you want, the more pre-cooling it's going to do. Now, there was a time where it wasn't all about energy, and it was about indoor air quality, and that was the main focus. So when we invented these wraparound heat pipes 30 years ago, the main focus was indoor air quality, and nobody knew what a wraparound heat pipe was, and we would go out and solve humidity issues in existing buildings by retrofitting their coils that would drive the dew point down, heat the air back up, and reduce the relative humidity out in space. So we still see that quite a bit. Today, the main focus is on energy savings. So neutral air is an ideal application. Neutral air generally needs more reheat. You're not sending such cold air out to the space. It'll get too cold. Dedicated outside air systems, makeup air units, very common for that kind of application. And again, the more reheat you want, the more savings you're going to get, because that's not just more free reheat, but more free cooling on top of it. The more outside air, generally, the better. We see a lot of 100% outside air systems. If it's all outside air, then since we're a sensible device, it's all based on the delta T, and the more outside air usually means a larger delta T, so we'll do more energy recovery. And that also generally means there's more humidity to be controlled and more moisture to be removed when there's more outside air. We see a lot of chill beam systems as well. Chill beam systems rely on primary air that needs to be at a lower dew point so that the beams themselves don't condense water out in the space. And as we showed before on the site chart, putting a wraparound heat pipe on a coil allows you to further depress that dew point and do it a little more economically than having to go to a more expensive low dew point specialized type system. So we see quite a bit of chill beam systems these days. And not as much underfloor air out there as there used to be, but if you're doing underfloor air or displacement ventilation, you know that you still have to dehumidify the air just the same, but you can't send air out in the 55 degree area out at your feet. You definitely feel that it gets too cold, so you have to reheat that air back up. And again, it's all about the reheat. The more reheat you want, the more savings you're going to get, the more the wraparound heat pipe makes sense. But what we're going to focus on today is utilizing the wraparound heat pipe to meet energy code. So let's jump into ASHRAE standard 90.1. First thing to point out is ASHRAE has this map of North America, and it breaks it down into climate zones. It's not showing it here, but the western half of the North America is what they call the B climates, or the dry climates, except on the Pacific coast. That's actually a C climate. But the eastern half of North America is what they call the moist climate, or the A climate. But either way, as you can see, the further south you get, the climate zones get larger and smaller and smaller by number. We're even down in Miami and Cuba, we're talking climate zone 1. So why does that matter? So the other thing it gets into is breaking down how much whether energy recovery is required based on the outside air that's needed for that system. And then it breaks it down based on those climate zones. So generally the more outside air that's required, the better chance there is that energy recovery is going to be required. So as you can see, all the climate zones A, all those moist climates on the top table, 1A through 6A, if it's 80% outside air or more in that air handler, you're going to have energy recovery. And as you can see up top, that's when that system is operating at less than 8,000 hours per year. If it's a 24/7, 365 operation, you got to go down to the table below where it's more than or equal to 8,000 hours per year. And as you can see, every climate zone in North America except 3C there will require energy recovery if it's at least 80% outside air. So what kind of energy recovery is required? Well, then you go into the meat of the section where it references those tables and references those climate zones. And it'll tell you that if you fall into that outside air requirement as shown in those tables, you will have to have energy recovery, and it has to be at least, and focus on the bold here in the bottom paragraph, at least 50% effective, and not just, heat pipes, we're sensible effectiveness, but per code, they're looking at total enthalpy. So whatever the total enthalpy there is available to be recovered, you have to be able to recover at least half of that. So what type of devices out there can recover at least 50% of that enthalpy? Well, the most common is a wheel, and we're going to focus on enthalpy wheels. But really, there are all types of wheels. You got your sensible-only wheels, you got your dehumidification wheels, and then, of course, you got enthalpy wheels that do a little bit of both. They're generally going to be about 70% effective or more. So they're the most effective energy recovery device out there, and fittingly the most common. There are, however, some downsides to the wheels. One, if it's a critical type application where exhaust air can't cross-contaminate or get back into the supply airstream, you can't use a wheel. It's also somewhat of a headache for a lot of maintenance staffs. It's moving parts. You got to maintain a wheel. A lot of times you got a motor. You got a belt. You do have a motor. You also have to bring the airstreams together. A lot of times that's not simple. Generally have higher static pressure than any of the other devices. You got purge to worry about, extra electrical work, and they don't really tend to last that long. So, there are many types of wheels, some better than others, of course, but generally they're going to last anywhere between 3 and 7 years, and that's, of course, very dependent on how well they're being maintained. A very good product for energy recovery, but certainly has its downsides. Another device out there that will meet this 50% mark is these fixed plates. They're not as effective as wheels, but they're still up in the 60 to 70% range. There are plates that can recover both sensible and latent heat, so they'll meet that enthalpy mark. No moving parts, so you don't have to pull any power to the plates like you would a wheel. They don't have cross-contamination concerns like a wheel would, so you could use them in those scenarios. Downsides, however, probably the biggest is just they take up a lot of space. Most cores max out at about 5,000 CFM, so if you have a high volume system, you need a bunch of those cores, and they're not small, so you have to make sure you have plenty of space for them. They're not very easy to clean, so from a maintenance standpoint, they're not moving, so that concern is out of the way, but they're not easy to clean. Owners don't look forward to replacing them, so they certainly have some concerns as well. Static pressure not as high as most wheels, but it's still up there. And they're probably going to last a little bit longer than wheels, but still probably no more than 10 years or so, maybe 5 to 10 years, again, depending on the quality of the plate and how well it's being cleaned and maintained. And of course, and I spoiled this earlier, so I apologize, but there is this thing called a heat pipe out there that will hit this 50% mark. Upsides to it, no cross-contamination, a lot more durable, going to last quite a bit longer, sometimes up to 30 years, even more, depending on the kind of conditions it's in. They certainly don't take up a whole lot of space. They're going to look just like a coil. And they are, we're generally going to be above 50% effective when it comes to energy recovery. Now, I say effective, again, we're talking sensible effectiveness. So the biggest downside to the heat recovery heat pipe is that, yes, we're 50 to 60% sensible effective, but from a code standpoint, they're looking at an enthalpy change. And when we need to focus on enthalpy, that 55% would equate to roughly 40% effective on enthalpy. And that's in heating mode. So if we're looking at cooling mode, we're factoring in latent load. That effectiveness drops even worse. It's cut to about half depending on the type of conditions we're in. So we can hit 50%. We're going to need to go up to an 8-row heat pipe and really look at the conditions and may need to reduce the face velocity. But we can hit that 50% mark depending on the conditions and what we're able to put out there. However, 90.1, that energy recovery requirement, does have some exceptions. And as you can see, it's a nice list of 9 in the latest 2013 version that covers everything from applications like labs and kitchen hoods and different climate zones you're looking at. But the one I want to focus on here is the final one, number 9. If the system is using what they call energy recovery in series with the cooling coil for dehumidification, then that qualifies as an exception, and you don't have to do anything else as far as code is concerned. So the next question, what is energy recovery in series with the cooling coil? Well, that is exactly what the wraparound heat pipe is doing. It's recovering heat upstream of the cooling coil and then wrapping it around in series with the cooling coil and redistributing that heat as reheat. So know that if you're in a tough spot, or whether it's difficulty in pulling ductwork alongside the outside air, or you've simply got no space for one of the cores, or an owner that doesn't want a wheel, or an engineer that doesn't want to use a wheel, their options are not going away. The wraparound heat pipe is there and will meet code. So know that putting that wraparound heat pipe in there will meet code all by itself. No other energy recovery is required. So what I want to do now is show you that depending on where you are and what kind of application you have, not only is it a way to meet code and a nice alternative system to the typical approach, but you may actually save more energy using the wraparound heat pipe. And again, this is depending where you are and what kind of application it is. And as you'll see, it's all about the reheat. So I'm going to look at here our home base in Tampa, Florida, basic 10,000 CFM system, 52 degrees off the cooling coil, local utility rates of 10 cents a kilowatt, and then $1.50 for a therm of hot water. And we're going to assume here that the air is to be discharged and reheated up to 65 degrees for this application. So an enthalpy wheel in Tampa, Florida on a summer design day, which we would call 95-78, is going to do about 9.33 BTUs per pound of enthalpy change for you. So again, it's not just sensible cooling, it's latent cooling. So it dehumidifies and cools the air, as you can see in the top portion there. The wheel's, of course, not going to give you any reheat unless you got DX. Whole different story if it's DX and you got outgas reheat. But if it's a chill water system, you're going to have to pay for that reheat elsewhere. But the benefit that the wheel gives you is that when it's cold outside, it's going to preheat that air. So that's what that bottom is showing you, that on a design day, it's not only going to reheat the air, but if it's an enthalpy wheel, it's going to humidify the air a little bit as well. So put that on a table. That, wheel's generally about, we're going to use one that's about 71% effective. At 10,000 CFM, this wheel is adding a little over an inch of static to each airstream. Take that fan static into account, not to mention the motor to keep it turning. That wheel is consuming about 4.4 kilowatts to run at 10,000 CFM. If you use Tampa weather bins and those utility rates I mentioned, you can see that you're going to get nice cooling savings. Not only is it cooling the air, it's dehumidifying it as well. Not as much of a heating season down here in Tampa, Florida, obviously. This is why people like to come in here and visit when it's cold. But you're still going to get about $3,600 in preheat savings. Unfortunately, the electrical penalty does get up there. I mean, 2 inches of static plus a motor to keep it turning, that takes away from the savings, but you're still looking at about $9,200 in net savings in this scenario. Now let's look at the wraparound heat pipe. Much different site chart. We're pre-cooling the air, but again, it's sensible cooling only, so it's just straight across. Not as much of an enthalpy change, not even half, about a third. And we're not going to do any preheating. In heating mode, the heat pipe is essentially off because the delta T from pre-cool to reheat is 0 because that cooling coil is not on. So in heating season, it's not doing anything, but we are going to get you all that reheat. Whatever pre-cooling we're giving, we're equaling that on the reheat side as well. So it doesn't look as nice just looking at the site charts compared to the enthalpy wheel, but it's a whole different story because of the location we're in. So now, certainly not as effective, especially with 2 rows, only about 30%. But now we're going to reheat the air up to 65 degrees whenever we can. 2-row is sized in this case so that at 95-degree design day, it's reheating 52-degree air up to 65 degrees. So at design, it's getting up to that 65 you want. As design day gets cool and we start hitting part load, it's not getting you 65, but it's still giving you as much reheat as it can. But the static pressure is quite a bit less. I mean, instead of an inch on each side, we're talking not even 4/10 of an inch total between the two. So the static pressure is quite a bit less, so the fan power is going to be a lot less. We're looking at 0.7 kilowatts. So as you can imagine, the cooling savings are about a third as the wheel. But the key is, one, the reheat savings. Even though we're dealing with smaller delta T's, we're dealing with a lot more cooling hours and therefore reheat than the enthalpy wheel is able to do. On top of that, that small fan penalty leads to a much smaller hit on the electrical side. When you add all those up, you're actually looking at savings that are a little bit more than the wheel. You take it a step further, and again, this is just an example. I'm using Tampa, Florida. I'm also assuming 65 degrees is okay. Each application is going to be different, but just trying to paint a picture here. But if we were able to use a neutral air condition and go up to 4 rows instead of 2 rows, well, now we're actually going to heat up to 72 degrees on our design day, so you're getting a lot more free reheat, a lot more free cooling. Static pressure is going to be worse because we double the amount of rows, but you can see that just in a neutral air condition with the amount of free reheat you're getting, especially in a place like Tampa, Florida, where there's a lot more cooling hours, those savings go up tremendously over either the 2-row or the wheel could offer. On top of that, the first cost, this may surprise some people, but the first cost is either a benefit or the same. An ERV is going to cost you about $1.50 a CFM. 2-row wraparound heat pipe, we're not, and these costs are not counting any electrical work that's needed for the wheel, any additional duct work or anything like that. I'm simply looking at first cost for the device itself. So the price to just for a 2-row wraparound heat pipe, about $1 a CFM. So not only are you going to pay less for it, but depending on where you are and what kind of application you get, you might actually save more as well. And even in neutral air, we've doubled the amount of rows. It's going to cost about the same and save you a whole lot more. Now, I'm sure you're sitting there, if you're not one of our listeners that are in the state of Florida, you're probably saying, yeah, but this is Florida. What about us up here and wherever we are? And absolutely, you are right. Even if I just go up to Atlanta, Georgia, it's already a different story. The amount of cooling hours drops, the amount of heating hours go up. The cooling savings go down, the heating savings go up for the wheel, they go down for the heat pipe. The electrical penalty is not going to change, but as you can see, an enthalpy wheel versus a 4-row is going to save you more energy over the year. So even in neutral air condition, the saving is going to be a little bit less. This is when I would argue that, well, yeah, there's other additional first costs involved, but more importantly, year over year, it's certainly going to cost more maintenance-wise when it comes to a wheel than it is a heat pipe. A heat pipe's just another coil to be cleaned, nothing extra in there. But they also, then I get into lifespans. I mean, if the wheel's going to last, let's say 5 years, and a heat pipe's going to last 25 years, well, you've replaced that wheel, 4 times before you have to think about replacing that heat pipe. So that's when the differences start to even out. And again, I'm not claiming that the wraparound heat pipe is going to always save more energy than an ERV. That would be way too bold of me, but I am showing that, depending on where you are and depending on the application, besides the benefits of going away from pulling the air streams together or having something out there that there's no space for or an owner doesn't want or the engineer is not comfortable with, there is an alternative device by meeting that exception to energy code, and you may just save more money and not spend as much or more to get it. Of course, further north than Atlanta, it's even a much more different story. This is when I would argue actually using a wraparound heat pipe in combination with something doing some sensible energy recovery, so that you do capture energy on the heating season. Of course, I'm biased here, so I show our heat recovery module doing that. But anything doing sensible recovery in the winter time is going to give you energy recovery then. And by adding the wraparound heat pipe to it now in the summertime or when it's cold, when it's hot outside, you've actually got 2 layers of pre-cooling that's really going to dehumidify that air nice and neat and give you a really efficient system. So we see this quite a bit, especially as we start creeping up towards and above the Mason-Dixon line, or especially on low dew point systems like chill beam systems. It gives you your energy recovery when it's cold, plus it further depresses the dew point when it's hot. So now I want to shift gears and talk about if you've decided that the wraparound heat pipe is the way to go, then let's figure out how to truly optimize that system and get the best bang for your buck. And that's where controllability comes in. So what we can do with our wraparound heat pipes is put some solenoid valves on them so that you're able to stage these circuits off and on as needed. So we're able to stage them into up to 3 or 4 stages. So if you look at this picture, let's just assume there are 12 valves there. If you had 4 stages of controllability, we would not take the top 3 valves and make that one circuit, because then when you turn that circuit off, and now you've got stratified air coming out of the heat pipe. So we would actually stagger these valves, and every 3rd valve would add up to be one circuit. So we'd stagger the valves so that when we stage them off and on, you're still getting a uniform temperature out of the heat pipe. And the way they're controlled, it's a nice simple sequence. It's kind of the opposite of staged electric heat. I like to think about it. Instead of when you need more heat, turn on a stage of heat. After an amount of time, when you need more heat, turn on another stage. It's the opposite. We're going to go ahead and recover that heat and give it to you as reheat. If it starts getting too hot, well, then we'll shut off the first stage of circuits to reduce the amount of heat we're recovering and reheating. And if after a certain amount of time it's still too hot, well, then let's turn off the next stage of circuits, and so on, and in reverse when it starts getting too cold. We can also do some modulating valves. So if you've got a large system, the more rows you have or the taller the heat pipe is, the more circuits you're going to have and the more valves you're going to have. So it might get to a point where the amount of solenoid valves in there is just unbearable and unattractive. So what we can do is take this. We actually use this for our split passive heat recovery when the air streams can't be pulled together. We can actually separate this up to about 40 equivalent feet. But we can utilize this as a wraparound as well and it allows us to, we actually have some vertical tubes in there and then some headers, vapor up top, liquid at the bottom, combining those vertical tube circuits into common headers going back and forth from pre-cool to reheat. And allows you to use those modulating valves in the liquid line. Just be careful. There are some downsides. One, it costs more than a basic wraparound. But two, those headers take up space in the airstream, so you're going to reduce your coil face and therefore increase face velocity. But you also need to be concerned with the fact that these are vertical tubes and therefore you have horizontal fins. Horizontal fins are fine when it comes to just air-to-air heat recovery, but when you're talking dehumidification, it can lead to that condensation not running off the fins as well. So if we've got 4 rows or a lot of outside air, or even modulating airflows where the velocities could get down, you might actually see a buildup in condensation that won't go away. So it's certainly an option, but one that we wouldn't just float out carelessly. We always want to look at that with you and make sure that we aren't going to have any issues before we decide to go that route. So any interest in one of those systems, let us know, and we'll work it through and see if it makes sense. But why would we control it? Well, if there's a downside to the wraparound heat pipe, it's that you may not want that reheat. And, you know, the hotter it gets, the bigger the delta T, the more heat we're going to recover. So the more pre-cooling you get, and that's great, but the more reheat you get as well. And generally speaking, when it's the hottest outside, that's probably not when you want the most reheat. It's probably the opposite. So just simply putting control valves on there allows you to control that leaving air temp a lot better. And that in its own right, having that controllability is a great benefit for having these control valves. But what I want to focus on is really utilizing these valves to optimize the savings on the heat pipe by not focusing on a full load day and that design day, but focus on part load, because that's where you're going to spend most of your time. And what it does is it allows you to somewhat oversize the heat pipe, get the reheat you want during part load where you're spending more time, but then trim that reheat and cut off those circuits at those fewer design days so you're not overheating the place. So I'm going to take this same scenario, Tampa, Florida, 10,000 CFM, same utility rates, 52 off the coil, and in this case we're being told that we don't want to leave the unit warmer than 65 degrees. So again, that 2-row non-controllable heat pipe at design day is reheating up to 65. So you can actually put this in there, not put any valves. It's never going to be too hot. You're not adding a whole lot of static. We budgeted about $1 a CFM. And in Tampa, Florida, with those rates, you're going to save a little over $10,000 a year with a nice 1-year payback. This is a nice, easy application, assuming 65 degrees is as warm as you want. You're never going to have to shut it off. The downside here is you're only maximizing the amount of free reheat you can get on design day. And that design day does not happen very often. We're spending about 1 to 2% of our time down here in the 90s. So on the flip side, let's say we oversize the heat pipe. Now we're certainly going to exceed 65 degrees on our design day, and then we add control valves to it so that when that happens, we're not overheating. So a 4-row controllable heat pipe is actually going to reheat the air up about 17 degrees, which is of course too hot. That's when we'd use the valves and trim those circuits down. It's adding about twice as much static. It's got twice as many rows. We're going to budget this twice as much. So not only are we doubling the rows, but we've added valves to every circuit. But the real key here is that we've sized this so that on an 85-degree day, now we're getting 13 degrees of reheat and hitting that 65-degree mark. So now instead of maximizing the amount of free reheat we can get for 1 to 2% of the time, we've maximized the amount of free reheat we can get 25 to 30% of the time. And then as that cools, we're going to get more reheat than we would have before. So we're saving a lot more energy. These energy savings are taken into account the trimmed reheat. So I'm not counting 69 degrees of free reheat in that scenario. I've trimmed that reheat out, and we're still getting about $13,000 in savings. So even though it costs twice as much, the payback is still just a year and a half. But we've increased your savings by about 20%. So after a year and a half, you're going to save 20% more energy than you would have just by leaving it as a non-controllable system. So don't just look at it as getting free reheat and sizing it at full load. Focus on that part load. Really optimize what you can get out of it. In addition to this, this is again showing a fully controllable heat pipe. That means we've got a valve on every single circuit. And that means that if at some point in time you're going to want 52-degree air discharged out into the space, plus whatever fan heat's coming on it, if you're going to want that cold air at some point, then yes, a fully controllable heat pipe is what you'll need. But if you're going to want some reheat all the time, well, then why would we put valves on every circuit? You're now paying for valves you don't need. So we can do what we call a partially controllable heat pipe. So let's take this 4-row, and instead of putting a valve on every circuit, let's put a valve on half as many circuits. So the first thing you'll see is that we're actually reheating more. This is because when you add valves, it adds friction to the refrigerant circuit within the heat pipe, and that friction takes away from the heat recovery. So if you have half as many valves, that's essentially half as much friction, so we're going to get better heat recovery and more reheat more of the time. So again, we're trimming the reheat at design day, but now at a day like closer to 80 degrees outside, we're going to be able to maximize the amount of reheat we can get. Static's the same, it's still 4 rows, but it's going to cost less. We got half as many valves to pay for, but it's also going to save you a lot more energy, again, because we've got half as many valves taken away from the heat recovery. Now we're back to that 1-year payback, and we are saving more than 50% more energy than you were before. So the takeaway from this is, one, if you want to just put a wraparound heat pipe in there to meet code and just get what you can, there's certainly nothing wrong with that. But if you're truly wanting to capitalize how much energy can be recovered, that's where the control valves come in. Use it to size the heat pipe for part load, trim the unwanted reheat at design day, and think about using a partially controllable heat pipe if you're going to want some reheat all the time. And you will notice if you get into our software, a controllable heat pipe is available for you to select, but a partially controllable is not. So if that's something you're interested in, talk to your local rep or give us a call, and we'll help figure out the right way to do it for you and help you figure out those energy savings and make sure for yourself that it makes the most sense. Finally, a quick spiel on our company itself. I'll give you the elevator speech. Again, we've been around for about 30 years. Our founder got a grant from NASA to figure out a way to take these things called heat pipes and utilize them to enhance dehumidification. And a year later, the wraparound heat pipe was born in his garage, and we started as a company, and that's where the wraparound heat pipe came into play. Some years later, about 3 years ago, we were purchased by a company called MyTech, which is a Berkshire Hathaway company. So yes, we are Warren Buffett approved, and we moved to Tampa, Florida shortly thereafter. If you'd like to come visit our facility as an excuse to come visit Tampa, we have no problem being the reason behind that excuse. Come and see us. We make heat pipes that are prepackaged and shipped out to the air handler manufacturers. We call them U-frames because when you look down on them, it looks like a U. But it's a nice prepackaged heat pipe so that all they have to do is slide it into their air handler, flash around the edges, put the panel back on, and it's good to go. But we also retrofit air handlers here, so a lot of times, especially for jobs down in the southeast, or if the modification price is too high, ship that shipping split to us with a cooling coil in it. We'll install the pre-cool and the reheat separately, circuit between them. As you can see in the picture in the top right, we've added some sheet metal upstream of the cooling coil to prevent any air from bypassing around the cooling coil and condensing on the back side. So we'll do that for you here. You can see the picture in the bottom left has some solenoid valves. All that stuff is done in-house, and then we'll put it back together and ship it on out to the job site for you. Of course, we also do site retrofits. whether it be retrofitting an existing unit that's having humidity problems or just needs, they just want to save some energy and avoid all the reheat they're paying, we'll come out there and do it for you. We also do this on a lot of jobs where the shipping splits have to be small to fit into a tight clearance or tight door to get into a room. We can install the pre-cool in one split, the reheat in the other split, have it go out to the job site, put the air handler together, then we'll come out there and circuit it up and charge it and get it together for you. So just wrapping it up, pun very much intended. The wraparound heat pipe, not only is it going to save you energy and all the reheat, but it is an exception to energy code, and that was the main focus here. Utilize the fact that an exception is using energy recovery in series with a cooling coil. You don't have to worry about anything else. It will meet code on its own. They're installed in the factory, whether it's ours or air handler guys, or we'll do it on the job site. Chilled water, DX, doesn't matter. We do it all. The more outside air, generally the better, but even a recirculated air system. If there's humidity to be controlled, the way the heat pipe looks at it, that's always a 20-something degree delta T, so there's always going to be some free reheat and some free cooling as long as you want it to be done. Still going to save you some money. We don't take up a whole lot of space, only a couple of inches here and there on all around the cooling coil, so we fit into most systems, especially chill water, some DX, and a quick return on investment. I mean, obviously the examples I gave might have appeared on the little extreme side, but even if we're just adding 5 to 10 degrees of reheat and in a climate that's certainly not as favorable as here in Florida, you're still going to see, again, based on utility rates, return on investments is somewhere in the 2 to 4 year range, generally speaking. And of course, make it controllable. To really optimize the amount of energy savings you can get, that's what the valves can be used for, not just that added controllability, which in its own right has some value, but focus on that part load and truly save as much energy as you can. Last but not least, don't take my word for any of this. I assure you I'm an honest guy, but if you go on to Select Plus, our software, you can run all this stuff yourself, plug in all your conditions, get drawings, site charts, run the bin analysis, plug in your city, plug in utility rates, and see for yourself what kind of payback you're going to get, and does this make sense for you or your client. And that's it. So at this point, I'd like to open it up. I know some questions have been coming through here and there. I urge for anyone who's still there to stick around because, one, we're going to have some survey questions. I'd love some feedback on that. Or can you answer that right now, those survey questions? Yeah, okay. So go ahead and answer those if you can. That'd be great. And also, if for anyone who's a PE and looking for PDH certificates, shoot me an email at the email below, and I'll make sure to get that to you this afternoon or as soon as you get those to me. And actually, I must have been really awesome because I only have one question here. And if any more pop up, feel free to send them to me. Let's see. Any chance to utilize microchannel for higher efficiency and lower cost? Scott, there is certainly a good question. The problem is we've kind of designed our system around the typical copper tube, expanded into fins type approach. I'm not going to say that we won't do that someday, but I know a lot of general coils have gone that route. But changing that design is not in our R&D plans right now. But that's certainly a good thing to point out and something we'll keep in mind in the future. But I can tell you that we have no immediate plans to change up our coil design, so to speak. But I appreciate that question. Any more pop-up, John? All right. I must have answered everyone's questions throughout, so I appreciate everyone for joining us today. We'll try to do another in the series of A Wonderful World of Heat Pipes later on this year, so keep an eye out. And thanks again. And again, exit questions and those answers would be much appreciated. And we'll see everybody next time. Thanks a lot.